Okay, welcome to Lecture 4. Today we're going to start on Chapter 2, which is fluid statics, meaning fluids that aren't moving, or at least not accelerating. So what we're going to do is start today with a definition of pressure. How do you find the pressure? And then once we have that information in fluid statics, then we can apply that pressure to surfaces that are submerged over the whole surface, figure out what is the force. Okay, so thinking about the force, let's say you dive down to the bottom of a pool. You might have some ear pain, right? Something's going on. Well, what's going on is inside your eardrum, you've got atmospheric pressure. You quickly change the pressure outside, and now you're going to have a net force, and that net force is what's going to cause your pain. Okay, so basically, if you have a different pressure on two sides of a surface, you're going to get a net force. Okay, so that's very important, especially say you're working on a dam. You need to know what pressures are on that dam in order to build it strong enough, right? You could do the same thing if you think about you're in an airplane and you go up or down in that airplane, change your altitude. You're going to get that same kind of problem with your ears, but it takes a whole lot more depth, doesn't it, to get that painful ear problem. And you can alleviate it by somehow opening the connection, some kind of tube between the two sides of your ears. If you can open that up, then the pressure will equilibrate and the pain will go away, right? So turns out the pressure in a static fluid is going to depend on what is the fluid. So in diving down in the pool, you got a lot bigger pressure change very quickly. It's also going to depend on the depth of the fluid. Okay, and what's going to end up being true is this equation. After we go through a bunch of where this all came from, this is what we're going to come up with. So the change in pressure is going to have to do with the change in height, and we're going to call that Z, and the fluid density. Okay, so those are what are going to be important in our problems here, finding pressure. So a couple things to remember about pressure. Pressure always acts normal to the surface. So it's opposite of shear stress. It's a normal stress. Okay, and it always acts towards a surface. Okay, so if you take a pressure and figure out what force that pressure is causing, that force is always going to go straight perpendicular towards the surface. Okay, but a point in a fluid, pressure it doesn't have a direction. It's just a pressure at some point, kind of like shear stress in a fluid is just a shear stress at a point. Okay, therefore pressure it's not a vector, it's what we call a scalar. Okay, it doesn't have direction. Okay, now the force due to the pressure, force is always going to be a vector. It's going to have direction. Okay, couple of definitions that we're going to use quite a bit. First one is specific weight, and the symbol for that is gamma. Okay, and that is weight per unit volume. Okay, so if we do weight, W, per unit volume, like that. Now let's just break that weight down. Weight is M times G, right, over volume. Well, M over volume, that's rho. We tend to work in rho, not M, in fluids. So our final equation for gamma is rho G. Okay, and that's very useful because if we go back to the equation on the previous page, look at that, rho G is right in there. So instead of having to look up rho and then multiply it by G for all your problems, you can just look up gamma usually. And that'll make your life a little bit easier. Something else you're going to need to know is specific gravity. Specific gravity is just a density comparison. So it's a ratio. So you're going to get a 0.8 specific gravity or a 1.5 specific gravity. So what it's defined as is it's the density of whatever fluid you're talking about or solid that you're talking about, divided by density of water. So this works for liquids or for solids as well. For gases, it's going to be the density of whatever fluid you're talking about over the density of air. Okay, so it means different things if you're talking about a gas. Okay. So, for instance, mercury, which has the symbol Hg, has a specific gravity, mercury, of 13.6. So mercury is very heavy. It weighs 13.6 times the weight of water. Okay, so it's compared to water. Times the weight of water. Okay, so you could also do this with gammas. So gamma over gamma of air, right? Because you would have a G in the numerator and G in the denominator as well. And you could do the same thing for the liquids and solids. So on to absolute and gauge pressure. We already saw this in thermo, but here's just a bit of a review. Absolute pressure is referenced to zero molecules, meaning zero absolute pressure is a perfect vacuum. Gauge pressure, on the other hand, is referenced to 1 atmosphere, so zero gauge pressure means 1 atmosphere. Okay, so if you have gauge, which a lot of times you do, you have gauge pressure and you're trying to get to absolute pressure, what you want to do is add on 1 atmosphere. So for the number for gauge pressure is always smaller than the number for absolute pressure. So if you have gauge, you're going to add 1 atmosphere to get absolute. If you have absolute, you want to subtract 1 atmosphere to get to gauge. Okay. Usually you're adding to get to absolute to use in some sort of equation. So just to remember, 1 atmosphere happens to be 14.7 psi or 101.3 kilopascals at standard temperature and pressure. So that's the number. So if you have a gauge pressure of 10 psig, add 14.7 onto it and you'll have your absolute pressure. Okay. Gauge pressure can be negative, but absolute pressure can never be negative because you can't have less than 0 molecules. Okay, but if gauge pressure is negative, sometimes what we do is call it a PSI vacuum. So 2 PSI vacuum is the same as negative 2 PSIG. In other words, it's 2 PSI below 1 atmosphere. So that would be 12.7 PSIA. In formulas where you're multiplying pressure times something, doing anything except for subtracting pressure, you've got to use absolute pressure. Sometimes you don't know which one it is just by looking at a problem. So if you have a homework problem in homework, if it doesn't specify, just like in thermo, assume it's absolute. However, if there's some sort of problem and it says a gauge reads this, or you're actually reading a gauge, what you're going to get is gauge pressure. So gauges normally give gauge pressure. That's why it's called gauge pressure. Okay, except for barometers, which are what measure atmospheric pressure. All right, so stop here and go ahead and do quiz problems 1 and 2.